Now, Greg, you on deck?
I am,
Yes. Wrong Greg.
Introduce yourself. Greg Bailey.
Hello. Yeah, am I audible? I have to check.
I can hear you. I can hear you now.
And is the audio listenable too, or is it screwed up?
Yes, I can hear it just fine. Anybody object to his audio quality? Silence gives consent. Light the fuse.
Is that screen legible to anyone?
Not very.
It's a result of sending a 4K screen across this kludge here. Well, at any rate, we're not going to be looking at it in great detail, but you can enjoy the crap there. I am Greg Bailey. I am the president of GreenArrays and have been for some years since our unfortunate loss of our CEO, Chet Brown, became unable to serve really in any practical sense in about the end of 2009. We are continuing to scrape along. We would still like to have a real honest-to-God customer. We still don't have enough money to give people officers. They can't. Bill, just a moment. Bill, go away. Go away. We still don't have enough money to give people offers that they cannot refuse. And in order to keep the doors open, sort of, they're basically cracked open. We're spending as little money as we can per year, and we are doing constructive things that we can do without spending a great deal of it. So I just was going to run over a couple of the things we've done this last year. One of them has been a heat propagation study. Chuck went to great lengths simulating temperature rise on transistor junctions. And over the years, we have never been able to measure the expected results of that. We've never been able to actually measure the effects of transistor junction heating on anything that we could actually observe. And that includes in simulation by other people's simulators, and that makes us wonder about the reality of it. And it's useful to wonder about because that takes a lot of work in our simulator. So we instead decided that we would find out how long it takes for heat to propagate clear across our die. And that's an interesting little undertaking. We can actually, in software, produce a thermometer that has pretty damn good repeatability and sensitivity and does not change what it's observing. In particular, what we do is we take a node on one edge of the chip and we have it wait for a pin to go high. It's pulling the pin low with a weak pull down, which is a very weak N transistor equivalent to about a 40K resistor to ground. And so we let it just sit there waiting for that pin to go high. And of course, while it's waiting, it's not doing anything and it's not using any power beyond leakage. And the reason for that's simple. This is what our shutdown wake up circuit looks like an AND gate. That's about all it takes. If this signal is the one that says get the next instruction, we have to have the one that says we don't have to wait for anything. And if we do have to wait for something, this signal doesn't produce an output on that line. And so therefore we just stop cold in about 100 picoseconds, which is about 1 gate delay, that it takes us to say, whoop, we're not doing anything. And then when this signal finally goes high, whoop, we're going again in another 100 picoseconds. Now compare that to an MSP 530, 5 microseconds it takes to ramp its clock up and ramp its clock down each way. 10 microseconds of overhead time during which that sucker is using power. So our little temperature measuring node is not using any power at all while it's waiting for the stimulus. The stimulus is someone else needs to raise the pin for just a moment. And in this case, we're raising it by another J144 for about 30 nanoseconds. Well, this guy sees it rise, and so what he does is he promptly drives it hard, and begins a 1,000 micronext loop, at which time he then drives it low hard, puts it back on weak pull down, and waits for another thing. We measure that with a scope from outside, because that's a nice objective, more or less time invariant way to measure it. We could measure it with another chip, but then we'd have to calibrate that, and we'd be having the temperature compensate it and everything else. And so what we've observed is that we can sit there and, let's see, when we cause one of our nodes to produce that pulse, it is burning about 6 3/4 nanojoules of energy into the die, which is not an appreciable change in temperature. And we can observe that it isn't because we can take a node and make it repeatedly respond to these pulses. And as long as we're not making it respond to more than, say, 100 a second, we cannot measure any difference in the width of that pulse from the time we started that until the time we gave up. So those 6 3/4 nanojoules per measurement are pretty softly walking into the whole deal, laying a very small footprint. So what we can do then is start generating heat clear on the other side of the die with a node. It could be at a spin loop, or it could be, say, taking an output pin that we shorted to ground and driving it high. That latter takes like 7 orders of magnitude more energy and puts it into the chip than as heat than we can by doing our little temperature measurements, totally reducing our own effects to even more noise. All right. So the result of all of that was very interesting. We were able to observe that the heating from that one node shorting out its pin to reach the other side of the die took about 2 seconds for it to start being perceptible there, and it reached equilibrium in about 10 seconds. For cooling down, it took more like 20 seconds to become measurable, and somewhere between 1.5 and 5 minutes to reach equilibrium. This is a chip soldered to a board with the usual heat sinking capabilities of a regular PCB with multi-sites and multi-layers. So that was kind of interesting to learn. The reason why we can do this is that there's a fairly linear relationship between the execution time of a micronext and temperature on our chips. And it doesn't matter where in the process variability curve you are, and it doesn't matter much where you are in the temperature curve, as long as you can stand to be in the room with it. You're in a linear section of that whole thing. And so it's about 3 picoseconds per degree C of execution time for micronext. So if we do 1,000 of them, that's 3 nanoseconds per degree C. And sure enough, we calculate that the temperature rise we saw at the other side of the chip by shorting out a pin on the other side of it was on the order of 1.3 degrees C. All right, so there you are. Isn't it nice to be able to make a thermometer out of a piece of code? So that was good, clean fun, and we'll do more with that eventually. The thermal resistance looks like about 100 K per watt from that. That's very close to what, at least on the cool down, to what we estimated and put in the data sheet of 60 K per watt. So there we are. So that was the first thing that we did last year. And then after that, we've spent time making a new release of Array4 3 that was done last spring. Then we did a ring out test on the Volterra PCB manufacturing, actually a fabrication and assembly tool that we have. And it's a very nice little device. It's perfectly adequate for making prototypes and test circuits, so we like it. It worked fine, so that checkout passed. We've spent some time on the GPS project that we talked about last year. All of the correlators are now working just fine, and the FIFO to allow us to absorb samples at roughly 5 megahertz while we are getting answers out of the correlators and giving them new phase shift values are all coded. And so that works fine, and we're ready now to actually make a board for the RF section that we've already designed and laid out. And that's using a chip made by ST Micro. It's basically an RF front end and a mixer and a 2-bit A to D from the IF. So we're looking at 2-bit samples at 5 megahertz-ish rate. And so that'll be a lot of fun when we get around to it. Unfortunately, the folks that want us to do that still haven't given us a penny. So we have to do other things in order to keep the doors open, then simply hunker down and work steadily on that and nothing else. So it's just life. A large amount of time this year has been spent on finishing up the implementation of GLOW, which is our new CAD system. The hardware simulator is validated in the sense that exactly to the microamp and the attofarad, or excuse me, attojoule reproduces the results from OCAD. The netlist extraction works identically with OCAD given the same tile array. And so the next thing that we're doing is actually converting the G144 chip description to produce that tile array in GLOW. And so here, just for laughs, is some of what that looks like. That's just some of the middle of our chip. The dark green columns are in wells. The light green stuff is diffusion. They are in transistors if they are made on the white areas, and they are P transistors if they're made in the dark green areas. The red stuff is poly, making gates and providing a conductor where we have to use it for that. And the blue stuff is metal 1. Metal 2 looks like that. Metal 3 looks like that. Metal 4 like that. Metal 5 and metal 6. So this is the abstract version of the layout that we look at when we're designing. It's not exactly identical to what goes out in GDS, which is what's over here on the right-hand side of the screen. This is a comparison of the GDS2 from GLOW with the GDS2 that we actually made our chip from. And we can XOR the two together, we can verify that they're identical, and that's where we're headed right now, is to exactly reproduce the GA144 with the new tool. The new tool is a bit faster in simulation than OCAD was, and that's nice because that's what you do more of than anything else when you're designing. The simulator itself is very interesting. Chuck chose to do it at picosecond intervals. What we're doing is basically integrating differential equations brute force. We sit here every picosecond. We look at the IV curves for each of the 2.5 million transistors on the chip. We decide how much current in microamps is moving through that transistor, and we determine how many attocoulombs we are removing from one capacitance on one of our terminals and depositing on another capacitance on the other of our terminals. And we do this to all the transistors. Then we look at all of the nets that we have been moving these little charges on and off of, and calculate what the new voltages are on all those nets, and we do it all again for the next picosecond. And this is a fairly fine-grained analog simulation. It's nothing but an analog simulation. And for a computer whose typical instruction times are on the order of 1,400 of those steps, it's adequately rigorous, and it works pretty well. So it's a lot of fun to use, and it's a lot of fun to not have to pay for. It's a lot of fun to not have to pay for the outrageous prices of modern CAD tools. Incidentally, anybody that doubts that the communist Chinese steal things from the United States, we have direct observational evidence that they do. While we were doing a project in 2013-14, particularly in 14, for someone in Shenzhen, China, that person wanted us to do some work at 28 nanometers. In order to do that, we needed the latest and greatest version of Calibre from Mentor Graphics, which we could certainly not afford. That is software that costs 6 figures per seat per year for rental. So we asked this fellow to get us access to a machine that had the latest Calibre on it. The next day, he called up and said, okay, I've got one on my desk that's running it, and here's the IP address, climb on in, here's a login and a password. So our fellow, Dave, climbed in, looked around. Sure enough, it was the latest version of Calibre. And then he looked at the license file. This license file was an perpetual license to everything Mentor Graphics had, which according to Dave is a license that you can't even get from Mentor Graphics, but if you did, it would cost millions. And this joker of a tiny little company in Shenzhen, somehow or another had that license on a machine on his desk. Just flat ass amazing. But that's exactly why Dave can no longer make a living doing silicon verification, because people in communist China can outdo him because they don't have to pay a damn thing for their tools. So it doesn't really matter what the guy is charging for his time when the tools cost more than his time does, do they? Anyway, that's why we don't sell any of our chips into that country and won't. At any rate, what else can I add to this excitement? We have plans for next year. We're working on and waiting on authorization to begin work on the second part of the exercise of making a novel power supply in which our chip controls the whole thing from DC to AC on a pretty much sit there and run all day and not bother anybody basis, unattended. And it's going to be interesting because the conventional way of doing that has a lot more stages and a lot more inefficiencies. So with luck, we might actually get into something that's been built and distributed and used by people, and that'd be a nice thing. And we have an exciting educational initiative that I will hope to be able to describe in detail next year. So let me turn this thing off. Let's see. Did that turn off the screen share?
Yes.
Good, excellent. So, should there be any questions, I'm here to answer them. And if there
Greg,
aren't, I wish everybody well.
This is Brian Fox. I'm curious what the tools were we were looking at. Is that OCAD?
That's Glow.
That's Glow. Okay.
Yep. Both proprietary to Chuck and GreenArrays.
Okay.
Greg,
is it a further development of OCAD?
Yes.
Okay.
Greg, this is Greg Villa. Just a question.
Sure.
There was an interesting article on VentureBeat about a product from a company called Cerebras, with multiple CPUs, pretty much the G144 on steroids. It sounds like somebody's taken your work and Chuck's work and just marked it up to a bigger size.
Probably not. You see, because what is unique about us is not putting a bunch of computers on a chip. What is unique about us is that those computers are appallingly simple. When they're doing something, they cost very little energy per operation, like 7 picojoules per instruction execution, all right? And because it's a simple machine, that is why that's low. I mean, basically VDD squared C over 2 is what it costs you to change the state of a capacitance. And so the more capacitances you have to charge or discharge in a CPU per instruction to get it to do anything, the more energy you're pissing away that way. So to begin with, Chuck puts a minimal number of transistors there, and we carefully lay things out to minimize the capacitance of the wire. So each instruction uses very little energy, but that's not the end of the story. The next thing that happens is that we don't use those instructions unless we absolutely have to. We have very easy ways of stopping when there's nothing useful to do. Stopping on that 150 picosecond dime that I was showing you, which is not something anybody else does. And that, the business of being able to operate at a low duty cycle and still respond within, you are doing useful things when you get the stimulus in the first nanosecond. You're not screwing around waiting for things. You're not screwing around waiting for your clock to ramp up. And you don't have a clock running in the background to piss away energy when you're not doing anything. Those are important things. And those are the distinctive things. Everybody that I've seen who's made an array of computers has much more inefficient ways of doing the communication between them and every other little thing than we do. And finally, our programming methods are not to import giant libraries and try and use them to do things that they were never made for, like running at low power. None of these libraries was ever designed to minimize the energy consumed by that library for doing an operation. Show me the stat library where the cost of running a matrix inversion is documented to you in joules. And that's the way we think.
Perfect. You've explained exactly what I had in mind. Because from the specs on your website on GreenArrays, it said you only use 650 milliwatts for the GA144, where the Cerberus was using, I think it was 450 kilowatts, some crazy numbers to run the same thing.
Well, and that number that you just cited with the GA144 is with all 144 nodes running 100% duty cycle, which hardly ever can happen. The reason that we're so fast is that that's what falls out of this process. 180 nanometers falls out at being basically a 600 megahertz machine, is in terms of MIPS, right? We would have to put away more energy to slow ourselves down. It's a losing game to try and slow the computer down. What you do is run at the natural speed of the silicon until you run out of things to do, and then stop. And that's what we do.
Very clever technique that you speak about. Thank you.
A pleasure. Any more? Well, then I guess it is time to pass the baton. Thank you, folks. It's been a pleasure.
Oh, wait a minute.
Okay.
I posted my question in the chat, and I was hoping
Oh,
that
I'm sorry.
That's okay. I'll just read it out loud. Wouldn't a great application for the 144 core GreenArrays chip be as a Bitcoin miner platform?
No.
Which should be competitive on a cost basis of energy in to calculations out, because the silicon is running at full speed?
The answer, it wouldn't be, okay, for a couple of reasons. First, we make some of our biggest contributions to things by simplifying the algorithms that people give us to solve. Somebody gives us a problem description. I learned this from Chuck decades ago. The first thing you do is tear the problem description apart, because it's usually completely bullshit. It's usually some guy's idea how he'd do it. All right. And so there you are, writing code to this guy's ideas. I'm not going to do that. If he wants code written to his ideas, he can write the code. And generally, the reason why it's worth tearing them up is that usually it is a wrong-headed, inefficient, crappy way to solve the problem. So it's better off to return to first principles. That's Chuck's theme forever. Return to first principles. What problem is this guy trying to solve? And then we try and simplify how you can solve that same problem. The difficulty with a cryptographic algorithm like SHA-256 is that if you can simplify that algorithm at all, you have just discovered a weakness in the algorithm that will be of great interest to the crypto community. So here we are given a prescribed algorithm that is by nature not simplifiable. All right, second, a Bitcoin miner is running 100% duty cycle flat out all day and all night until his hardware no longer can produce enough money per joule that he has to pay for to justify spending the power on it. And that is not what we are superb at. What we are superb at is running very efficiently at low duty cycles. We're running at low duty cycles because we're a lot faster than most applications need. And so we're able to shut down most of the time. So it's not unusual to look at an actual thing that you could do with the GA chips that would have us running at a 10 or 100, a 0.1 or a 0.01 duty cycles. These are considerably different than running flat out. So are we as good as anybody else running flat out? And the answer is no. Especially not if, I mean, even if we laid out silicon, and we actually did, to do SHA-256, we would not have been competitive. Oh hell, we wouldn't have been competitive in 2012, because by then there were already faster processes available. Those processes would not be suitable for what we do because they also were extremely high leakage. But that's all right because they were running 100% duty cycle. Even if you tried to stop them, they'd be sitting there smoking, doing nothing. But you're never going to stop them because you're a Bitcoin miner. So you're 100% duty cycle all the time. Yeah, 14 nanometer FinFET is way more able to do SHA-256s per joule than we are. We're not at the limit of that axis. We're at the limit of the axis of getting useful work done for anything that doesn't require 100% computing, all right, for low energy cost. If that makes any sense to you.
I had a question.
Do more with less with the chip, though. So maybe I think there's an aspect of it you might not be thinking about. I don't know.
Well, no, I mean, we've actually done this, all right? We have designed such hardware. We have done Bitcoin mining with something that was doing SHA-256s faster than the GreenArrays chip ever could, all right? And we've personally experienced well, at least during fall of 2013, the spring of 2014, the difficulty setting for Bitcoin mining was basically adding a bit of zero in the hash every month, which doubled the difficulty, which reduced by a factor of 2 what you could earn per joule expended. And so we made $1,700 with this one fellow's FPGAs the first month. And the next month it was more like $800. And by the end of 10 months, it was, as you'd expect, 1/10/24 or so of what we made that first month, and it was no longer worth keeping the thing powered 24/7. And that's the nature of that game. It's a very brutal game. But that ramping up of difficulty is the only real security measure the Bitcoin structure has to prevent somebody from being able to dominate the mining and therefore start messing with the blockchain. The difficulty is kept high so that nobody can practically control 1/3 of the mining industry. They could, they can fork it, then you're screwed. Everybody's screwed.
I had a question regarding how does GA144 compare to programming on FPGAs in terms of like execution speed, energy, and also iteration speed? I imagine iteration-wise it must be a lot faster, but is it energy and like performance-wise, or are FPGAs?
Have you ever seen or looked at or thought about a clock distribution network?
Not really. I'm a total hardware noob.
All right. Well, okay. Here's what you've got to understand: VDD squared C over 2. Every time a clock line changes state, that is how much energy you just spent changing its state. You've distributed a clock all over a chip. You've got a huge amount of capacitance involved in that clock network, and it's changing state at whatever the clock frequency is continuously, and those VDD squared C over 2s are accumulating. That's VDD in volts, C in farads, and the answer is in joules. And it is just amazing. I mean, right, we laid out a clock distribution network just as a trivial example that was about what it would take at dead minimum to get a clock all over the an area of silicon equivalent to that of an F-18. And that clock distribution network already consumed more power than we could consume inside of our node. That is something you live with in an FPGA, because an FPGA is not a place to make asynchronous logic. You're not going to practically be able to do that because with a lot of the tools, you can't even control anything. You can't control the interconnects where the capacitance is. You can't control the strengths of the devices. You can't control anything that affects the time constants of signals. Also, some of the FPGA tools that the manufacturers provide intentionally randomize the layout every time you recompile it.
Oh.
Yes.
That's horrible.
So there's the problem. You have an intrinsically synchronous logic. Otherwise, all right, when you're comparing it with any other thing that you would do a synchronous computer with, it's not a bad way to do it for experimentation. And for implementing an instruction set, it's a way to emulate. Somebody can take the CPU manual from GreenArrays. Our CPU manual is uncommonly short. It's like all of 12 pages of substantive material. And you can certainly sit down and implement in an FPGA something that executes that same instruction set. In fact, John Reibel did it just for the hell of it to make life easier for some people that were working for Intelisys. And, you know, it's a thing you can do. It's no longer an asynchronous machine. So things like, for example, my little 10BASE-T Ethernet receiver, which is a one-node software Manchester decoder running at 10 megabits. It has no clock, it has no crystal, it has no nothing. It just sits there and listens to the Manchester coded bit stream coming in its pin and pumps out bits the other side, right? You cannot do that with any current processor because they're all clocked. You cannot get there and synchronize with that edge that you have to synchronize with to wait and find out correctly what the real data edge is that's coming. You can poll for it, so which now you're running at 100% duty cycle, and you're polling a pin that is probably not going to respond fast enough for a 10 megahertz signal anyway, because you're looking at 20 megahertz transitions.
Fascinating. Yeah.
And so we can go to sleep on the pin. When the edge comes by, bam, we're running. We clock off some time to make sure that we're past the noise edge the next time, and we go to sleep again. And that's the fun part about stuff like this, which you can only do with our chip or some other truly asynchronous processor. And I'm not sure that addresses what you're really asking either, but
it definitely did. It's fascinating. I had no idea that it was very hard to do asynchronous programming on FPGAs. Yes, that's
no. No, it's not asynchronous programming so much as asynchronous layout. You cannot lay out an FPGA yourself unless you are in bed with the manufacturer and have access to stuff they don't let people have through their normal tool chain.
Do you think that now that AMD has acquired Xilinx, the scene might change a bit? Like AMD had an open GPU architecture since long.
I don't know why, because academia doesn't think you can do what we do.
Clearly they're wrong. If I may, at this point, invite Greg to come back sooner than next year. I know we don't want to be a sink on his time, but we would like to keep, we'd like him to keep us posted on his progress, maybe shorter, more frequent presentations. Does anybody have anything for Greg that can't wait and is of immediacy and speak up?
I do. It's Don Golden, Greg. Good to hear from you.
Oscar was here first.
I'm sorry. No.
Don, wait. Oscar, speak up. Make it fast.
Thank you. Thank you very much. No, I just want to say goodbye because I have another compromise. It's quite late here in relation to Pacific time. So I appreciate very much the invitation and would like to follow up with it.
And we'd like you to come present to us, but we digress. Okay, Don, make it fast. Don, you're up. Make it fast.
I just wanted to say hello. And so, you use ColorForth, and then that generates, your CAD program generates the chip, right? So ColorForth is like Verilog, right?
No, ColorForth is nothing like Verilog.
No, I mean, no, what I'm saying is it's the high level language to create your, that ties into the layout tool.
Okay, we don't use ColorForth for this anymore. We're using Glow. What we're doing right now is exactly matching ColorForth's everything from the beginning to end so that we know we have not broken anything before we start changing things. What ColorForth, what OCAD and what Glow both do is they have a high level language that describes layout. It does not describe logic.
Okay.
It says, put a 2x3 P transistor right here and put a 1x3 N transistor over here and draw a polyline between them. You have now made a minimum inverter. Connect the power to these two terminals here connect these two up to here together, and now you've got one ready to wire up to something, signal in and signal out. We work at that level, but it's, of course, a high-level language. So once I've got a word for making that inverter, I can say it anywhere, and on and on and on. Pretty soon, I describe a register bit, and I can make 18 of them by just saying, do this 18 times. And that dovetails straight into the syntax for GDS, which allows you to replicate things like that. So,
well, thank you so much, Greg.
yeah, take
We're
care.
so grateful. And please come back sooner than next year. Daniel, are you on deck? All right, share your screen, light the fuse, introduce yourself. Thank you so much for your patience.
No problem. Okay, I'll start with sharing my screen. Good. I stopped the video, so